gotta love a class we're saying, let's do some Babylonian on the side. Actually makes sense. Babylonian number system. Can anybody tell me anything about it? Yes. Base 60. So the places look like 1, 60, 60 squared, or 3600, right? And you can keep going. Our base is 10. That's why our number system looks like base 1 times 10 base 10 times 10 base 100. So the places are built off of the base that we use. We didn't have to use 10 as a base, but we did. Okay, today we're gonna get to play with some shit. So I got my little thing. Makes me feel like I'm about to give you some food on an airplane. So base 60. How many symbols? Like for us, we have 10 symbols for our numbers, right? 0 through 9. You guys with me? How many symbols does the Babylonian for numerals? Let's say, because I did show you at least one other symbol. What numbers do they represent? Yeah, there's something that represents 1, something that represents 10. So officially it's a little triangle, but I'm going to let us just write a 1, right? And officially this is 2 of these little, and again, you can even imagine just somebody crank, and that's a 10, right? Bam, bam, 10. But for us to write the damn thing, I'm just going to let us write like a less than symbol, right? So it's always easier to go from somebody else's number system to our own. Let me show you what I mean. That number right there. How many 60s are in that number, in that numeral? 2 60s. So I got 2 60s plus how many ones? 11 ones. So then I can piece it together and figure out how we would represent that number in our numeration system, right? So this would be 2 times 60 plus 11. That's 131. Is that cool? So in our number system, our numeration system, the idea of 131 things, we represent it with these symbols. Babylonian, this is how they represent the idea of 131 things. They use those symbols. How we doing? Okay. And again, accept the fact that this is going to be weird because we are doing something that is kind of butting up against something so fundamental. You've known it since before you can remember things, right? You've known numbers. You've known our number system since before you have good memories. We are kind of messing with that. That's like so integral to our approach to any numbers, right? Yes?
Can you go over A on 22, A11B?
Oh, yeah, okay. Can you see how many places there are? Three places, everybody see that? You guys kind of with me? One giveaway with this, because this leaving a space really sucks, because how big of a space do you leave and all that kind of shit, but something that really gives it away is you would never see that in front of a that unless it was in a different place. You always put the 10s first and then follow with 1s. Does that make any sense? So that this must be its own place, this must be its own place, that must be its own place. So what are the places? This is the... No, this symbol is 10, I agree, but what place is it in? The 1's place? 60s? 3600. So how many 3600s do I have? 1 plus how many 60s? Do you see what I'm saying? So converting from somebody else's number system to ours will almost always be multiplication and addition. Going the other way is going to suck a little more because it's going to involve division and subtraction, which are inherently harder. Okay, is that all right? So if you understand what each place means and you understand the symbols, it just becomes a multiply and add problem. That's what it becomes. I have how many 3600s, I have how many 60s, and so forth. Is that all right? And again, the symbols are new. the idea of a base 60 is new. So don't feel bad if it's still difficult for you. I'm just trying to tell you, it's not, it shouldn't be, but it's just new to us. Yeah.
On C, what are the smaller triangles?
Oh yeah, so they do tell us in the book, this is the symbol for 0 that they created. So I think that's, I'm not sure if I said that, but I think I did mention, there. Placeholder. Do they actually, I mean, they have it here. So let me see if they give us an example. Here we go. This problem right here is a good one. So whenever you see these two triangles like this, that means there's 1, 2, 3 places where the middle one is empty. There's 0 of those. So this is the equivalent of 0 in our number system. And again, the symbol for 0 had to be created. The idea of 0 had to be thought out. I mean, which is weird to us, but you know, we're standing on the shoulders of a lot of math that's been developed. Okay. Is that all right?
Is it like just to keep the space?
Yes. So most of their civilization, they just would make a space, but that would lead to a lot of confusion. So eventually, they created the idea of what they called a placeholder, which actually we know of as 0. Right? Because you can't always, if you put a space, somebody else could copy it and not put the space, and all of a sudden you don't have enough chairs for your party, right? I needed 701 and you gave me 71. So does that, you see what I'm saying?
Yeah.
If we didn't have a 0, we had a space, 71 could very easily look like 71. So eventually they came up with,
Because it's not really a space. It's like
the space could, in fact, if you went 7001, do you just go, all right, here's a bigger space. I hope they understand what I mean, right? So instead you could put placeholder twice. So then I know you mean, does that make sense? I mean, this is such a beautiful, you are forced to think about our own number system more than you ever have before. So 0 exists. We're lucky that we live in a time that 0 exists, because it didn't exist, or it wasn't thought of at first. We had to come up with it. So Babylonians is an interesting thing because, like I said, you could actually see in their civilization when they came up with the idea, which is really kind of neat. It wasn't just there when their civilization took off. They had to come up with it, right? Today we're going to look at Mayans, and we're going to see what their symbol for 0 is. Right, Chinese, I love Chinese because the Chinese symbol for 0, the ancient Chinese symbol for 0, it looks like somebody sticking their tongue out. I really hope that's not, it's just neat to me. I just like that. So if you look up ancient Chinese symbol for 0, it does look like somebody sticking their tongue. There's the, just to give it away, there's the symbol for 0 in mine. Right there. Looks like a UFO or a mushroom, maybe? I don't know.
Looks like an eye.
An eyeball. Kick ass, I like it. Yeah. Turtle? Okay.
Oh, I see it.
Gemara. No, nobody gets that? Okay. All right, guys. Is that good for whoever asked a question? I just want to. Anything else? Okay, so let's do this. We got to talk about Mayans, and thankfully they're right here. This is nice. The Mayan place system is weird. So let me ask you. Let me see. How should I do this? Let's do it like this. I'll be up on the overhead today, I think. Scheisse. Oh, it's the most exciting part of the class. Okay, get out. Do I have? Oh, I can steal your paper. So if I had a base 20, it shouldn't be a big deal to us because we've already seen base 60. Base 20, what should that look like? What would the first place be? Ones. It's always 1. No matter what base you got 1's place. The next place should be 20. The next place should be 20 squared, which is 400. Is that cool? Don't worry, I'm going to get to mines. This is what a true base 20 system should look like, right? And then every time you just take another step up, you just multiply by another 20, correct? So you multiply by 2, and then you add another 0, basically. Multiply by 20, multiply by 2, add a 0. Okay. The Mayans liked the number 20, which makes sense. 20 is a nice number. 20 goes into 100, and there's a lot of factors of 20. It makes sense. But what they didn't like, what did we say before about civilizations that were really heavily based in agriculture? What's a very important number for them? 360 something, right? So roughly 360. So they're like, all right, I want the number 360 to show up in our number system. So let's do something really weird just so we can screw students over in the future. Let's do this. All right, let me do this one step at a time. Let's do this. 120, that's great. But now I'm going to multiply by 18. And you're all like, come on, nice. Okay. Because what's 20 times 18? 360. Which is roughly how long a year is, correct? Okay. And then they went, okay, and then we'll keep going with 20. We'll keep going with 20. So then they multiply that by 20. So double it, 72, add a 0. So this is 18 times 20 squared. So their number system is sort of base 20. Do you understand part of the reasoning about why it's not exactly base 20? And again, every civilization, they can make whatever the shit they want. They can do whatever the shit they want, as long as they can teach their people, or at least the rich or whatever, the educated members of the population, right? At least as long as they can understand it, and then they can communicate using it. They can do whatever the shit they want to. Are you guys kind of with me? Kind of? Like, for example, real quick, when I had people do a project and they had to come up with their own number system, I'll never forget a few people. One person made it based on frequencies of music. So it was like a civilization where they had, I can't remember exactly how he said, these aliens, and they had they could make all these different sounds perfect. Everybody had perfect pitch, and they had these little extra mouths that could make all these sounds. Are you guys sort of it? So if they wanted to say the number 87, they would make a frequency for 8 and another frequency of sound for 7. Do you guys kind of follow? And then somebody else made it based on color. So like yellow meant the tens place or whatever. I can't remember. You guys kind of with me? So it's wide open for whatever a civilization wanted to do. Okay, so this is unfortunate. I will provide you with the places on a quiz or a test. I will give you those. I'm not going to make you memorize this because it's not base 20 really. The next thing they did was they didn't put numbers like this. They put numbers up and down. So it'd be place 1, place 20, place 360, place 7200. Maybe. Some of you guys who have read ahead are looking at me like, that's what I saw. Okay. Now the symbols I kind of told you a long time ago because they're some of my favorite symbols. A dot is 1. So that's the first kind of symbol we've seen that didn't really look like the number 1. Egyptians had a rod. Babylonians had this thing that I kind of make look like a 1. Here we got a dot is 1. And then the only other symbol they use is a line. Who remembers what that was? 5. Good try though, I like it. So their number system is not explicitly based on 10 at all, except for the fact that 5 is half of 10. It's still sort of the idea. Here's 5, another 5. Okay, so it's based on 5. That makes some sense. 5 fingers, right? Okay, I like it. So watch this. If we could put these things together, if I saw this in Mayan, that number, how many places are there? 3 places. This is the ones place. This is the 20s, and this is the 360s. How many 360s do I see? 1. Plus how many 20s? 2 20s. Plus how many ones? 1 1. So 1 360, 2 20s, and a 1. So just put it together. So if it's a place value system, I don't care what the places mean, I don't care what the symbols mean, it's going to be multiply and add to put it into our system. Doesn't that feel like what we did Babylonians? Different places, different symbols, exactly the same math, right? Now, one thing the Mayans had going for them was from the beginning of their civilization, they had this symbol. What's funny is, I always got to remember, because my other book I teach from uses a different symbol for 0 for the Mayans, but it's basically this. To me, it always kind of looked like a loaf of bread or something, but. Oh.
Somewhere I saw that. So now
Okay.
I only see a conch
Probably. Conch shell. Yeah, conch. Anybody ever read Lord of the Flies? Did you have to read that? Remember the conch shell? If you're holding it, you can talk. If you've never read Lord of the Flies, it's not a prereq for this course. Don't freak out. I keep what's that? I'm sorry.
I did not
Bad
like
memories?
that one.
Yeah. Anything I was forced to read for English, I basically already didn't like before I opened it. So, I understand. Okay. So if I saw this, you guys got notes from this? Because I'm going to turn the page here. So if I saw this, what do you see, Jeff? I see one pancake with a blueberry. Okay. I see this little dude. And then I see this. I mean, you have to just step back and say, that is really neat. That is much more interesting than 1, 4, 7, you know. It's awesome. Blueberries and pancakes and a freaking muffin or something, whatever you would call it. That looks like, it kind of looks like unimpressed squigglers. Yeah. How many places are there? I see why you might say 4, because this is really close. So that's 3 places, right? So it would be really kind of evil if I saw something like this. I have to realize that's 2 places, right? Are you with me? But again, they sort of have some problems with their symbols as to what denotes the difference between the places. Okay. So there's 3 places: the ones place, 20s, 360s, and then it's just a matter of how many 360s plus how many 20s plus how many ones. The math is the same. Even though the symbols are vastly different, the place is really different. Place values. So it'll be 3 360s plus no 20s plus how many ones? 6 ones. Like it. So whatever the hell that is. So 1086. Anybody doing it? You guys have calculators? Don't forget the 6, right? I like it. Okay. Sweet. It's my one skill. I gotta show it off every now and then. Math. Alright. So, let's do this. Does everybody have the sheet? This is the one that on one side was this, and the other side was a stupid amount of problems that we're not going to do all of them. Anybody need this sheet? Everybody's got this sheet. Okay. If you need this sheet, tell me. I've got some extras. Not too many. So what I want you guys to do, and again, just to show you, all the symbols are at the bottom. I'll basically give you this. I put the, I don't think this book talks about the Chinese system, do they? We didn't talk about it. I think they have it in number 16 they put it. Yeah. Oh, here, look, here it is. Oh, jeebus. Sorry. Symbol for 0. Well, crap. You really can't tell what that is. Trust me, it looks like a dude sticking stuff out. Okay. So you got the symbols down here to reference. So I want you to do these problems. Do number 3, number 10, and 11, 15. I'm not gonna worry about you. Did I assign number 16? I did. Ooh, I'm so evil. I love it. No, I'm not going to talk about it. You guys can ask me questions. Number, yeah, well, I have to do one of these. Number 6, 34, and 38, and 43. Good Lord, this is a lot. Okay, well, let's just do those. So don't do all of them.
Are you turning them in today?
No, you don't turn these in at all. Yeah. So if you want to work with other people near you, you can. If you don't have a calculator, I don't either. Sorry, I left them at home. So. So this one. This is why I'm not going to make you memorize this. Yeah, what do little fish tubes mean? Fish tubes is 100,000, so that's 200,000 plus, what are the scrolls? 100, so that's 400s plus little heel bones. Yeah, 10, so that's 20 plus 1, right? So that'd be 200,421. Kick ass. Alright, so Egyptian is just kind of like, our expanded form is when you write a problem, when you write a number like this. So they just gave symbols to each piece of an expanded form. That's what they did. What about, let me go over number 6. So how would I write this? 10,000 would be what symbol? Pointing finger? Oh man, my least favorite. So I don't know. Every time I draw, it looks different. I don't know. Let me just draw like that, maybe. So 10,200, which kicks ass, because all you need now is 2 scrolls, right? So the Egyptians beat us in a lot of numbers, unless it's a number with 9s. Right? Yeah, which is a lot of numbers. So, what about the 2 here, the Roman numerals? Looking at number 10. CXLII. Before you even start doing the problem, you look for what? What's the very first thing you want to find? What's the Romans are additive except for when? Yeah, when there's a symbol for smaller in front of a bigger. So you look for any pairs where that's true. So that's not true here. Oh shit, right? So then that, this will be 100. What is this? Yeah, 50 minus 10. And of course this is just 2. So you get 142. Yeah. Is that cool? So when you have Romans, the first thing you look for is any pair where the first is a smaller than the second. Because that means subtract. Everything else is just add. What was, did I give you one like that? No. Look at number 12 real quick. What was that symbol above the V? What does that mean? Yeah, so this would be 5 times 1,000. So this would represent 5,000, right? So a little bar. And that's why somebody asked about, like, sometimes you'll see a Roman numeral like this, which actually sort of means 1,000, right? So that's why, no. Okay. All right, so what about number 11? Any pairs that I got to be careful about? CD, good. So CD. Oh my gosh. Okay. Oh yeah, I forgot to look that up. Damn it. I have to look up how Romans actually referred to numerals as they were talking to each other. What time are you going to be around? About MC. All day. So this would be what? Yeah, it'll be 500 minus 100. Is that cool? This will be 2,000. Pretty sure they didn't go that. Plus 30 plus 7. So it'll be 2,437. Bam. So if you were a well-educated Roman back in the day, if you saw that, you would know it meant this. Lock it.
I'm sorry, what did you get for 10 again? Was it 142?
Oh, for number 10? Yeah, 142.
Okay, thank you.
Okay. Number 15. Now we got to go backwards. What is that, 1964?
Mm-hmm.
Of course, I circled over the thing. I want to write this as a Roman numeral, so I don't think we went backwards yet with Romans. What do you think you have to look for to be careful about with Romans? Like, everything here is going to be relatively easy except for which numeral is going to give us a little bit of trouble. The 9, yeah. Because 1,000, okay, I know how to do that. M. 900, so I can write this, if you want to, you can write this as 1,000 plus 900 plus 60 plus 4, which seems like a waste of time, but then you realize that's 1,000 minus 100, right?
Yes.
So you can kind of show yourself some work if you need to, right? So then how would I write 1,000 minus 100? CM. 60. Yeah, 60 is 50 plus 10, 11. And then 4. Ivy. Sweet. Okay. Let's get Chinese. I'm going to let you guys try that out in the homework, and if you have questions, you can ask. So I'm not going to talk about it yet. Number 34. How many places are in number 34? So what's very different between the Mayans and the Babylonians in our system is we have a single digit in each place. Both of those other civilizations had multiple digits in places, right? So that makes it difficult. Somebody pointed it out. How do you know how many places there are? Really, it's just the fact that these are together, and there's a space, and these are together. That's one of the few ways you know that there are actually two places. Well, what are the places? This is the 1's place, and this is the 60's place. How many 60's do I have? 3. And how many 1's do I have?
9.
Good. 10 minus 1, I got 9 1's. So this will just be 189. Yes. So this is kind of nice. You gotta let this be nice. This is like a little puzzle. And some of you guys might be like, I really hate puzzles. I'm sorry. So what about going backwards? Now here's where things get interesting. We did talk about this one. Remember what I told you? In general, you should always go one more place, but I mean, this one's pretty obvious where you stop. What are the places I'm working with? 60's. So it's really obvious that's where I want to stop, because the next one's going to be stupid big, right?
Yeah.
216,000. How many 3600s take care of part of this number? 1. How much of the number do I have left? 79 left, right? What does this number do for? What does this place do for me? It can take care of 160 of that. So now I got 19 left. So now I got to write a 19 here. Now let me change it into the right numerals, right? The right, numerals, Jeff. So it'll be 1 space, 1 space. How do I write 19? There's 2 ways to do it. I could do 20 minus 1, or I could do 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Those both mean 19. Is that right?
I put it differently. I did the 10s make 20, and then I did the little line above the second 10.
Oh, this symbol specifically means
Okay.
minus.
Okay.
So the little bar, you'll only ever put a line over like the symbol for 1, and that together makes the symbol for subtract. Yeah. I like it. All right, so now the new stuff. What about number 40, whatever the hell it is, 43? I can do that on this paper. What places are we having here? The ones place, 20s, 360s. So then again, so it's always beautiful going from somebody else's to us. How many 360s do I have? 3 360s plus how many 20s? 14 20s. Is that cool? 4 blueberries, 2 pancakes, 14. And then how many ones? How many ones? 7. I love it. And where LL at? 280. 1367, maybe? Yeah? Yay! Look at a math person adding and shit. Alright. How you guys feeling about that? I mean, that's... When I first started talking a little bit about this, I could tell everybody's like, oh God, I mean, allow this to be just some cool ass symbols that we could have used. Right? This could be what our system looks like. And just a little bit of a puzzle. Let's do one of these. I didn't assign one of these, but let's do one of these. Let's do number 48. Shit. Is that 17,000? Let me write it down again because this copy sucks. 17,913, is that what it is? Okay. Whenever you're going from our system to somebody else's, you first identify what places you're going to need, and you always start from the biggest place, divide, see how much is left. Does that make sense? That's sort of the standard practice. I might show you, we'll talk about it later. There is a slightly different method, but right now, there's a. So if I'm going to Mayan, I can use a ones place. I definitely need a ones place. I definitely need 20s. What's the next place? 360. What would the next place be? 7,200. What would the next place be? Say again, sorry? 144,000. Do I need 144,000? By the way, how did I get 144,000? Multiplied 7,200 by 20, right? Except for that one place. Everything's by 20. Times 20. We want 360. Okay, times 18. Times 20. Times 20. So it is a base 20 system except for this one tweak they made. Okay. So that's just another way they got us. Besides the calendar they put together. Well, they're going to be freaking out about this in the year 2012. So I do it exactly, so I don't need this place, right? So you almost always want to go one place too far, trust me. So what's the first step I do? The math doesn't change. I take the biggest place and how many 7,200s go into 17,913? So that you can just, I'm not going to make you long divide yet. We're not going to do some long division, so. Twice? All right, so I need 2 of these. 2 of those would be, you could do it, Jeff. 14400. There you go, buddy. So if I do 2 of these, that takes care of this much of the number. That's the way I kind of like to look at it. Each place can take care of so much of the number. So how much of the number do I have left to worry about? 3513? Sorry? And then 360, what can 360 do for me? How many 360s go into there? 9. Now real quick, I want to show you something kind of cool. I want to show you, this is just a total side note. You don't need to ever do what I'm about to show you, but I just want to show you. Are you powered? No. Do I have another calculator? Well, shit, I'll show you next time. All right. man, maybe I can, yeah, let's see if you can survive. This is my Doctor Who thing. Real quick, watch this. If I take 3513 divided by 360, so that's how you got 9, right? And you kind of think the extra shit doesn't mean anything, are you with me? But let me show you what it means. 9 360s is 3240, right? So then how much of the number do I have left to worry about? Again, you can do this in count. 273, is that cool? You with me? Now watch real quick. This doesn't mean anything. Just if you happen to watch this is so cool. If I go back to 3513 divided by 360, the 9 is all we care about. Well, I take the 9 away, minus 9. Multiply that by 360, I get 273. Why does it make sense? Because what is all this shit? Isn't this the remainder?
Yeah.
If I divide by 360, that's the remainder. So if I take the 9 away and multiply that by 360, I'll actually see what the number remainder is. Kind of cool. Do I ever need to do that? Do you ever need to do that? No, I just want to point it out. It's kind of cool. This stuff actually means something, right? You guys with me? So again, you never have to do that, ever. I got the 273 the other way. So how many, I'm sorry, so what was that? That was 9 of these, right? So how many 20s do I need?
13.
Say again?
13.
13, good, because that would be 260, that leaves me at 13, so I need 13 of these also, is that cool? Okay. So now, and just like with the Babylonians, I use my symbols for the work, and then the last thing I worry about is converting it into the Mayan symbols. So 2 would be 2 dots or 2 blueberries. 9 would be, say again? Oh yeah, okay. Well, 9 would be,
One line or one dot.
yeah, 1 pancake and 4 blueberries, right? 13 would be 2 pancakes to make 10, 3 blueberries, that's 13 now, right? And of course, then I just do another 13. By the way, something we will not discuss is every civilization we've talked about so far did have symbols for fractions and decimals. Does anyone want to talk about that? No. Okay, fine. All right. That is 2-2. Done. So we're going to get into 2-3, and I want to show you some cool shit. Look. I mean, look at that. That is so cool. So let me build up to what the hell this means. This is not some kind of like board shit that they painted red. I don't know if anybody gets that? No? Okay. Resistance is futile? No? Nobody? Okay, fine. So let me show you a few things. You're not going to get to play with these. Too bad. I get to play with these. You get to play with something else. So you can see this is going to work. Is that the best I can do? So what I've got are, lay these out and let me see what you guys think these represent. Okay, where are, oh, there. Let me throw a big red in here. All right, so let me put big red aside for a moment. Look at this guy. This is kind of funny. I think we call these units, we call these longs, we call these flats, and we call this a cube, obviously, right? How many of these yellow bits makes one of these? 10. So obviously, what number system are we dealing with? What base? We're dealing with base 10. So you can show a student very simply that if you put 10 of these together, let's see if Jeff can count. I'm not good with numbers. Let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you put 10 of those together, you can replace it with one of these, of course, right? And it's a beautiful visual. And I am sorry this is not showing up too well. Let me see if this helps out at all. No. Okay, is everybody with me? That's a really nice visual for a student. You can count, and they love it. Once they learn how to count, they want to show that shit off. So like, count these out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That makes one of these, correct? And what does that relate to in our number system, of course? Once I get, that's 9. Once I put that there, what does the fact that it becomes this mean? What number does this represent?
10.
So how many longs does it take to represent 10 bits? It takes 1 long. How many little units does it take? Do I have any units left over? Nope. So this is the number 1, 0. 1 long, 0 these dudes. That's why the number 1, 0 means 10, because it's 1, 10, no ones. Right? Okay, I like it. So of course, if I put, I don't know, 10 of these things together, what is that? 4, 8, 9, 10. If I put 10 of these together, it makes one of those, right? You guys are right. Okay. Now obviously, what you're currently doing is you're not learning based on, you're just learning, okay, you gotta understand these manipulatives and how to best use them with your students. So one way we do, and of course, if I put, you know, do I have enough? If I put 10 of these bad boys together, it's going to make this guy, right? So the really cool thing is, this is 10 to the 0. This is 10 to the first. This is 1. This is 10 squared. There's 100 things in here, right? This is 10 cubed, and it is a freaking cube. Isn't that neat? Okay. One reason why we call it a cube is because it's length with height, 3 dimensions, cube. All right, so what you're going to get to play with, so first thing I need from you, let me see. 3, 4, 5, 6, 7, 8, 10, 12, 14, 16, 18, 22. Oh, so close. I want to make groups of 3. And it's not going to perfectly work. If you need, I need you to make groups of 3. You're sort of not going to have to work together if you don't want to, but just to make it quicker to pass some stuff out. So can you guys make groups of 3? And if I need to help, I can. Groups of exactly 3. This one person will be unfortunately left out, but I will give you stuff directly. Blue is volunteering to be left out. Oh, no you're not. Let me see. Yeah, there's 3. You guys need another person, right? Who's back there? Are you guys together in the back? Yeah, there you go. Okay. All right. Let me see. I'm not going to wheel this sucker around. So just accept my gift as a group and just sit there for a moment. Never say I didn't give you anything. Blue, I'm going to get you in a minute. Did you leave anybody out? Everybody got one? All right, Blue, you get a ton of them to play with. Look at that. So, looking at these pieces, can you, whoever got that, can you please give, shit, let me see if I remember. I want you to equally divvy up the various shapes. I also still need to give you something else too. Let me just leave that here for a moment. Oh, this kind of, there's just no great way to quickly give this out. So, let's see. And then the really exciting part is going to be, yes? What did I do? Oh, that's going to be an exciting part. What's up? Oh, okay. Thank you. Each of you get 2. And I think I have a, yeah. Neat. Poor little dude. You would work out to figure out what number that is, correct? 34, same way. 45, same way. You with me? What 2-digit number does not follow that convention? There's a series of two-digit numbers that does not follow that convention. The teens. So every single thing, 20, 30, 40, 50, they're all number of tens, number of ones, kind of mimicking our places. Are you with me? Now this is something you probably never really thought about. If I follow that same convention, so if I have 5, 10s, 50, so it's a little shortcut for 5, and T means 10. 6T, 7T. I mean, come on. What should the number 1, 2 actually be read as if I use the same convention? In 12, how many 10s are there? 1. So how about 1T2, 1T3, 1T4? Are you with me? In fact, you couldn't really blame a student if they learned 20, 30, 40 and they went back and they said 1T2, 1T3 because they've learned the pattern. And it's very strange. It's very, there's, every time I teach a class, it's always hard for me to figure out how much and which history to include. How much time do I have to talk about the history? So for example, I could talk about why does the square root symbol look the way it does? Why did we pick the letter X? Why is that such a special letter, right? All this kind of shit. What does my shirt mean? I don't know, right? So with you guys, there's a lot of, oh my God, there's like history going back millions of years, and then of course involving math, and then there's history that goes back just a few decades. So I'm always curious about the, and I think I told you guys, I've never taught elementary school, so part of me feels like a poser to a certain degree because I'm teaching you the math for elementary, and I've never taught elementary school. So I'm always curious about the curriculum, if it ever, I've seen some of it, but how much history it injects into the lessons. You can't blame them if it's not too much because you can lose students' interest pretty quickly. Okay. What was the other thing I want to talk about? Oh yeah, what's the highest, like this number, what is that? That's 1,000, right? What's this? Million. What's this? Billion. This one is trillion. Anyone know what the next one is? Quadrillion. I love it, right? And they actually, there's names for even beyond that. So unfortunately, we do have to go at least this far to talk about our deficit, right? For example. Okay, I like it. Something else. Do you guys, anybody here come to the U.S. Later in life? If you want to let me know. Did you come from a country? Some other countries use, instead of commas, their commas and their points are flipped. Mm-hmm. So I sometimes will have students, back when I taught like Math 88, I really miss teaching Math 88. Such a cool thing, where I get to teach them 2 minus 7, stuff like that, right? I would very often have students from other countries where they wouldn't really understand what the hell that meant, and that was a whole hurdle in its own, right? So when you're teaching whatever grade you're teaching, you could very easily have students whose families have come from other locations. Something as basic as, well, that's pretty damn basic. Just what symbol do you use to represent a really large number? Does anyone know, just to bring this up, just because it's part of this discussion, this is our standard way to do long division, correct? Does anyone know a different way?
Is split.
Yeah, so in some countries, and again, Blue, I'm going to have to ask you, every time I taught my Math 88 or something, I'd look to see if there was a student in there, and I'd ask them to show me, because it's not something I'm used to. So almost every time I'd say, can you show me that again? Because I forgot how. So yeah, there's in other countries, they actually kind of like flip this, and it's more this way, and the numbers, I can't remember, you'd have to show me. So again, later this semester, we're going to learn why the long division algorithm works the way it does, right? And in other countries, they just chose a different way to organize things, correct? So almost every aspect of our mathematics, our symbols, our processes, the way that we set up things could have been different. And in some countries, they are different. Okay, sorry. There was one other thing, and I can't remember what it was. There was one. No. Shoot, okay. So if I ask you guys, do this. Can you see very easily, if you were suddenly teaching a student, if I laid this down and I said, like what number does that represent? You can see much more clearly now why it involves multiplication. Right, so if I have, basically this is the number 222, correct? Base 3. So now you can see exactly, so I have, this 2 represents the fact that I have 2 flats. But of course each flat represents 9 units, which is why we do 2 times 9, and so forth. So using this manipulatives really makes it much easier to show why the math is the way it is. This would be 2 9s plus 2 3s plus 2 1s. So this will be 26, I believe. So how can you verify that with a student? You can just have them count 1, 2, 3, 4, 5, 6, 7, 8, 9, and then when you get to the end, you're going to get 26. I like it. So let me ask you this. Since we're on the idea of bases, let's transition to generally how to just convert between bases. Let me see. I need some paper. My kingdom for paper. Here we go. Sort of. Okay. So let me see what you guys think about this. So it took forever to give you guys all that stuff, and I really didn't have that much to do today for that. Okay. Let's say this. Let's say that I've got, let me ask you a couple questions first. Can anyone identify what is wrong with the number I just wrote down? And then when I wrote a little subscript, that means what base it's in. Is there a mistake in that problem?
It doesn't have the number 5.
Yeah, the base 5 doesn't have the number 5. The highest single digit base 5 uses is the number 4, correct? So I do sometimes give a problem with, can you identify what the issue is with this number, right? And if you get this answer for base 5, that just means you did some math wrong. You didn't divide, you didn't have a big enough number that you divided into, so forth. So that's not good. How could I convert this number into base 10? What's the first step? The first step is basically the same. Anytime I'm going from somebody else's system to my system, I want to identify what the places mean. So what does this place mean? 1s, 5s, okay. 1s, 5s, 25s, 125, okay. So going from anybody else's to ours is always multiplication, addition. Very straightforward. So this would be 3 125s plus 125 plus 4 5s plus 1. So what's that come out to be? It looks to be 375 plus 25 is 421, maybe? I believe. Okay. Nobody's going to help me. Thanks. Okay. You're on your own, Matt boy. Why does it make sense that the digits I need to use for base 5 are bigger than what I need for base 10? Right? I need 421 for base 10. That represents the same number of things as 3141 base 5. This is 3141, this is 421. Why is it always going to be bigger in base 5 than it is in base 10?
Because less 5s are going to fit the spaces than 10s are going to fit.
Yeah, it's easier for base 10 to take care of a bigger chunk of the problem with each place. This first place can only take care of 125. In base 10, this place would be 1,000, right? Okay. Now, let me get you guys thinking about this. What about base, let's start with that. Base 12. What would be exceptionally weird about base 12? What did we say about base 5 just a minute ago? What's the highest single digit I need in base 5? 4. So that's easy. I just ignore 5 through 9. It just doesn't exist in base 5. That's easy. This is not, because what does base 12 require? I need a single digit representation of every number up to what? 11. How do we write 11? How many digits do we need to write 11? Shit. So I'm going to tell you two things. What I really dislike, one thing I don't like about this book is it says this. It says 1, 2, 3, great. We get up to 9. The next number would be 10, but we need a single digit representation. It really should be A, but they use T for 10, I think, if I remember correctly. Yeah. Okay. And then, this is so weird to us. I know, this is beautiful. So we can represent the idea of 9 with a single digit, but the idea of 10 takes us 2 digits to represent, correct? Base 12 needs those to be single digits. So then we just have to come up with a symbol. And I know you guys that, let me see if I can do this real quick for you guys. Let me see. Nothing is very quick here. I'm not even sure. I want to show you something real quick, and then I think I'll call it a day here in a minute. I said something about this. So I think it should be 1, 2, 3, A, B. So A would mean 10, B would mean 11. So before I show you this, I'm going to give you a little problem in base 12. So if I saw this in base 12, 1, 3, A, base 12. What are the places? 1's place, 12's place, 144's place, right? Just multiply by the base each time. So then you just piece it together as always, but now when you see A, so it'll be 1, 144, plus 3 12s, plus how many ones? 10. Now in the book, you're going to see, I think, and Ryan, you said you looked ahead, I think they use T and E for 10, 11. The reason I wish they used A, B is because for base 16, we use A, B, C, D, E. And let me show you one thing, and then I'll let you out of here. See if this will work. Don't worry, I'll switch over in a second. See if it'll work for you. Can I still do that? Damn it all to hell. Let me see. Ah, cool. Okay. Shoot. Oh, here it is. Beautiful. Go back. Go away. Okay, beautiful. All right. So back in the day when I was first learning how to create websites, create web pages, what I would do is I'd go to a website that I like. Grossman's website, I don't necessarily like, but it was there. Do you see down here? Let me kind of, can I zoom in on that? Let me see. Zoom this. Oh, it does get bigger. That takes so much ass. Can I give this more space? I can't. Do you see where it says color and it's got F3, F7, FA? See, 10, 11, 12, 13, 14. Yeah. So for base 16, you would need A10, B11, C12, D13, E14, F15, correct? And I don't even know if you really understand what that means. I really want to make sure you understand what that means. Base 10. We need single digits up to 9. If we had been evolved with 11 fingers, I guarantee you we would have a base 11 system. Why do we have, the reason we have 9 single digits is because when I get to a full set of fingers, I have 1 full set of fingers, 0 loose fingers, right? So if I had 11 fingers, I wouldn't reach a full set of fingers until I got to number 11, correct? So 10, we would have developed, it wouldn't be A, we just use A because we would have developed another symbol for 10. Just like we have a symbol for 7, we have a symbol for 5, we would have developed a single symbol for 10. Is everybody with me? So since that didn't happen, and we want to imagine base 16, for example, we say, okay, the symbol for 10, it could be A. Symbol for 11, it could be B, right? You guys kind of with me? So if we had evolved with 16 fingers, number one, glove makers would just make tons of money. But number two, we'd have a base 16 system. This actually is called hexadecimal, which is what we call base 16. It's a quick way to say this. This is a way to identify a color. Each element represents 0 through 15 possible amounts of blue, amounts of red, amounts of so forth. So F means the color that they're using has a bunch of whatever this might represent yellow.
I think it's every 2 digits for one color.
Maybe. I always forget this now. But I at least wanted to show you one place where we're actually using the stuff that we're talking about, these other bases. So there's one use of base 16 is to help us get more color options. So I can code colors. So if I went in there and changed this F to a 1, the color would change on the web page.
Would it change for everyone or just for you?
If I actually changed the code on the page itself, it would change for everybody. Now, listen, this code I'm viewing. Trust me, I can't edit this.
Oh,
right?
okay. I thought you could.
But you can go to any website and actually view the source. It used to be called view source.
Could you do it right now? Wouldn't it work right now for every SKU?
For my instance, I don't think I can. Let me see if I can edit this. Well, I guess maybe I can. Let's see. No, I can't. But I could copy it, and then I could edit that, and then it would only be on my computer. Right?
Yeah.
Okay. All right. I think that's plenty. So what I need from you is a little bit of help. Let's see. What's the best way to do this? Oh, this is terrible. Could you guys, I'll tell you what, could you guys just put all your stuff back into the cup that I gave you? I'll worry about,
Including the words?
if you can fit the ones, yes, that's fine. That'll make this, I think, the quickest way to do this. Yes, the ones give you like grains of sand, I like it. Put that cup up here, yeah. Yep. Yeah, thank you. So you can bring the blocks up and then. Oh yeah, there's flats and cubes. Yeah, you're good. Just put it over there. Thanks, man. If you want to put your blocks, your cubes in there,
Yeah.
coolness. Oh yeah, thank you. And then you can just put the cup on the tray there.
And then the ones in the